So I guess I will continue talking about the freshening of the Irminger Sea, as Ivan nicely introduced the topics for me. Thank you. And this is the work I've been doing with Fiamma and Jamie Holt, and I would like to express also a special thanks to our ongoing collaborators, Isabella Lebras from Hui, Amy and Heather, Leah McRaven, Penny Holiday, and Loic Hopert, who helped me to put all the mooring data together and made this talk possible. And why I want to start talking about why we care about studying the salinity, the changes in the salinity, and we are always, and of course, we're interested in trying to verify what are the impacts on the AMOC, the aboriginal heat transport, of course, and also based on recent research by Marilena Ottmans, for example, freshwater events, strong freshwater events can impact heat and freshwater surface fluxes with the atmosphere, and also impact the atmospheric circulation over the subpolar gyre. So it's a very important interest in trying to quantify those things. And what I mean by recent, when I say recent freshening of the Irminger Sea, what do I mean by that? And I'm talking about the last 5 years or so. All right. So here we have the Romanek and Gilson monthly climatology, average salinity over the Irminger Sea between 2004 and 2020 for the Argo Array time series. And here we have the 100 decibars, 250 decibars, and 500 decibars area depths. And you can see that in the first 10 years or so of the time series, you don't have much of a freshening over the Irminger Sea. However, after 2016, we start seeing an acceleration, a strong acceleration in the freshening, as we can see in this time series there. Now, how much of acceleration we are talking about? Here we have two maps. One is the salinity rate of change between 2015 and 2020 in the left. So you can see here the Irminger Sea has a strong freshening of about between 0.03 to 0.032 PSU by year. And of course, we know that this is a big freshening event that came out the Labrador continental margin and propagate out counterclockwise along the subpolar gyres with the subpolar circulation. So those are the same calculated from the Argo climatology for the upper 200 meters, and you can see the negative fresh water, the negative salinity anomalies starting around 2015 in the Iceland Basin, and then crossing the Reykjanes Ridge towards the Irminger Sea on the upper ocean. Now the little triangles here are the OSNAP array, and the green box represents the moorings that we are gonna talk about later in this talk, right? So just to have an idea of how accelerated this freshening if after 2015 is. So Tesdal and colleagues in 2018 quantified from the same climatology and other data sets that the 2014-2015 Irminger Sea salinity trend is about 0.01 plus or minus 0.002 PSU by year, mainly attributed by freshwater fluxes passing through the Denmark Straits coming from the Arctic, okay? Which is, in our case, it's at least twice or 3 times larger than that. And the average is 0.02 PSU for a year. Now, those are the moorings. In this little panel here, I show the moorings that I'm gonna talk about. So we have the CF mooring array near Cape Farrell. offshore, we have the the M moorings arrays designed to observe the deep western boundary current, and we also included the OOI flanking mooring arrays to have a better idea of what's going on. And one thing we can see that from the moorings, and this is still in the upper ocean, in the upper 200 meters, the salinity anomalies. You can see the freshening is arriving at the East Greenland current and Irminger current on the other side of the Irminger Sea around April of 2017, and a little bit later I mean peaking in 2019 in the interior of the Irminger Sea around the OY flanking moorings locations. Now, just to have a better quantification on this freshening, on those anomalies, you can see that here we have 3 moorings, one over the shelf, the continental shelf, another one near in the boundary current domain, the East Greenland current and Irminger current, and the flanking mooring B, which is this one, which is near in the central Irminger Sea. So you can see the freshening going on really quick, really rapidly over the western boundary current, and peaking a little bit later with a slower and freshening from 2017 and peaking on 2019 from the flanking moorings. Now, the magnitude it's smaller than what is observed in the Iceland basin, for example, which is approximately 0.2 PSU, but it's still a quite significant salinity trend and negative anomaly. Now, another thing is that supports the idea and the Argo data that this freshening event is not coming directly from the Denmark Straits, is that in the over the continental shelf, we don't have apparent freshening over the past 5 years or so. It's actually coming from the Iceland basin. And if you go and look into the microcats from the mooring arrays at those locations, we can also verify, and of course it's expected that, especially because the subpolar gyre is an important area for convection and deep water formation, that these anomalies wouldn't stay constrained to the upper ocean, right? In fact, it's propagating downward in the water column. This little box is the same time period in the other map, in the other plots, from starting in April of 2017. And you can see that even for layers deeper than of that dense potential density of 27.65 kilograms per meters cube, we can see this freshening going on after 2017. So the timing is convenient. And of course, this can be locally transported downward via deep convection. And this has been shown before for several authors. But what about in the TS space? What that means for the water properties, water mass properties. So as Ivan showed before, we have a maximum going up to down in the water column here in this TS diagram from CF7. You can see that we have fresher waters in the right at the surface, and normally we would have the subpolar mold waters, which came from the subtropics. It has an origin of the maximum salinity has origin in the subtropical gyre, and came to the subpolar gyre. And as we go, and those profiles are color coded by time. So you can see after 2017, where we have the greenish to reddish colors, we don't have this maximum anymore in the upper ocean. The water mass, the produced water mass, is completely different, with completely absence of this maximum of salinity. And this freshening is also expressed in deeper water masses layers. So you can see, for example, here in the area of the intermediate, Irminger Sea intermediate water and Labrador seawater domain, you can see this very sharp change in the salinity and completely change in the form, and the shape of the DTS diagram. Below that, below 2000 at 27.8 kilograms per or the ISO modified ISO layer, we don't see much going on. Now, if you look at deeper in the water column, we start seeing also changes in the Denmark Straits overflow waters. And this is the same TS diagram here, but now for the flanking mooring B at the center of the Irminger Sea that catches the plume of the Denmark Straits overflow water. So you can also see this freshening of the DSOW. And this freshening is convenient after it starts happening after the 2017. This is the same Hove-Moller, but now for the Denmark Straits overflow water domain. And you can see the freshening, the negative anomalies hitting 2017, however, peaking around 2019 or so. Now, the natural question that arises is, is this freshening related to the upper ocean or not? Well, Manish Devana and show that, and he's preparing a paper showing that in the Iceland basin, entrainment of the ISO plume can lead to the freshening of the deep layers, at least in the Iceland basin. So if a similar entrainment argument is valid for the DSOW, Denmark Straits overflow water, are the time scales and freshening magnitudes consistent with the evolution of the plume, for example? So it's one open question that we still need to figure out what's going on. And the eastern, another point that I want to make is that the eastern Nordic seas has also been impacted already by the freshwater anomaly described by Penny Holliday in last year. So is the DSOW formation region also affected by that? So I want to summarize what we have been found so far. We saw the unprecedented freshwater anomaly originated in the Labrador Sea, affecting the Irminger Sea in the upper ocean. However, is not constrained just into the upper ocean. We had enough time for the deeper layers to be affected as well. And what we want to study now, using Argo and global drift program data, so we are trying to figure out if the surface and subsurface advective time scales and water spreading patterns make sense, and if we can explain this freshening just by these waters being advected along the subpolar gyre circulation. We also have trying to understand more the impact throughout the water column of this event. If you have any questions, thank you.
I have a question.
Okay, go ahead.
I was wondering, Tiago, if you saw any amplification of the salinity anomaly when you compared the original salinity anomaly on the continental margin of the Labrador Sea and the salinity anomaly later on that you observe in the eastern subpolar gyre. Do you think that changes in the North Atlantic current have also contributed to that building up on the original anomaly, or do you think it was mostly an export of the original anomaly towards the eastern subpolar gyre?
That's a very good question. I have no concrete answer for that yet. But one thing we can know is that there's at least a amplification of the signal once this freshening signal gets to the central Irminger Sea, especially if you're looking at the flanking moraines A and B from the OY in the middle of the basin. And this is also true for the Argo data. I suspect this is related to the feedback from the atmosphere. So when we have a fresh water anomaly like this, we increase the storm, the precipitation over the Irminger Sea, basically. And I think that's happening. Now, if there's an amplification related to the shift of the subpolar front, for example, in the Iceland basin, I don't know yet. I don't know. Probably there is, which is probably well. It's related to how long this event can last. Like it's lasting for years now, so I think there might be a relation with that.
Thank you.
Any other questions?
Hi, Tiago. Sorry, I just missed this. What is the timing like for the freshening of the Denmark Strait overflow water? In terms of, is it?
Yeah, the maximum freshening starts happening, the acceleration, the maximum acceleration, it's just before the peak, So it's after 2019, we see this maximum freshening. But the water layer, the Denmark Straits overflow water layer, it starts freshening since 2017 or so.
So about the same time as you see.
About the same time, yes, yeah. Exactly. It's about the same time, but the acceleration, the maximum acceleration happens after 2019. Where you can see our big drop in the salinity over this layer, dip layer.
Can I ask a quick question?
Yes.
Hello. Yeah. Well, thank you. I'm Damien Desbruyères from Ifremer. And well, thanks for your talk, and also thanks to the previous speaker. I was just wondering whether you looked at temperature signal at the mooring, and whether it shows some kind of similar pattern in terms of sharp changing like this.
In the upper ocean, there is a cooling. So you can see here, for example, from the flanking B, you can see there's a cooling going on. You can see that there's not only freshening, but there's also a cooling associated with this freshwater event. Now, at depth, in the Denmark Straits overflow water, there's a slightly increase in the temperature, although it's not as prominent, but there's a slight increase in the temperature in the DSOW deep water layer.
Okay, thank you.
No problem.